this before we get started. This is a synthesis of the antipsychotic drug risperidone. Used to treat like schizophrenia. Last reaction choose to give the drug is this here. Labeled as SN2. This amine, the secondary amine. We've got the substrate with the chlorine, potential leaving group on a tetrahedral carbon. And you see now the nitrogen is now bonded to the carbon in place of the chlorine. So this is a good old SN2. Good nucleophile, yeah. These electrons can displace the chlorine, concerted SN2. Is this thing on? Can you hear me?
Yeah.
Question. What's the potassium carbonate, the sodium carbonate for? Sodium carbonate for? Because after the nitrogen displaces the chlorine, there's an H there, right? There's an H there. That's a plus charge. Right? What's the base for? Take the H. Base takes the H, leaves behind the neutral product. Okay? The nucleophile has to lose an H here. It's neutral to begin with. The bigger question I want to ask you is, what's the potassium iodide for? This we haven't talked about. Sort of subtle, a little bit kind of a tricky thing here to do. Why potassium iodide? It's very common to use that. Iodide. This is iodide. Iodide is the important part. What do you know about iodide? It's huge. What do you know about it in terms of nucleophile? Good nucleophile? It's a great nucleophile. It's also a great leaving group. Actually, it's one of the best nucleophiles around and one of the best leaving groups. Iodide is often used sort of as a catalyst because, see, this is a little sterically hindered. That's not a great leaving group, chlorine, right? But it's probably cheaper to make, especially on an industrial scale. Well, this can come in here and kick off the chlorine, and then you have a compound that has, that's all that ring, iodide on there. Now we have a better leaving group on there. Now this can come in and kick off the iodide. You just throw in a little iodine, you get that to take place, because iodine displaces that easily. Now this is more reactive toward the amine. When this gets ticked off, you get this plus what? Plus I minus, catalyst, it's reformed. That's often a very tricky way. You put in iodide to replace your chlorine. All you need is a very small amount, because it just acts catalytically. But it's a great it's probably a better nucleophile than this, and it's also a better leaving group than that. That kind of makes sense? Often used to sort of activate, make your SN2 reaction a little bit easier. Let's look at different reactions. Any questions before we get started? On Tuesday, we'll probably look back at mass spec. We had 3 compounds to assign to spectrum. Hopefully, you all know that. I know many of you have been working on that. We also may have a guest come by to tell us a little bit about mass spec. Question?
The weaker the base, the better the nucleophile, right?
No, not necessarily. No? Why do you say that?
Because weaker base would be more stable. Like iodine would be more stable, so it would be.
In that case, iodine is a weaker base than F-,
Right.
and it is a better nucleophile. But that's just with the halogens. I mean, weaker base, better nucleophile. I mean, water's a weaker base than hydroxide, but hydroxide's a better nucleophile also. Your statement is not universal. Let's look at these. Okay, what'd you get for the first one? We got this compound with the bromine, stereochemistry, heated in water. What's it going to give? If I propose a product? What'd you get? Plus an antigen. Okay. Is it going to be unimolecular or bimolecular? That is, it's going to be SN1 or SN2? SN1. Why SN1? That's secondary. Strong or weak here? Weak. Okay. Can you do SN2 with a weak nucleophile? So it's going to be SN1. Can you do SN1 here? Hopefully that answer is yes, because that leads you SN1. Can you do SN1 with a secondary halide? Yes, look on the previous page. This looks like SN1. Since it's SN1, what's the first step in the mechanism? Ionization to give the carbocation. Trigonal planar. It's all planar here. Planar in the board. That's your rate determining step, ionization. Then what attacks cation? Now the lazy nucleophile will get off the sofa and attack the cation. And we get, I'll make that phenyl. We now have, okay, that's planar on the board. It's flat like the board right here. Flat like the board. Is it going to attack from the front or the back? Both. So we're going to get this where it attacks from the front. We get that. But we're also going to get where it attacks from the back, and we would get that. The H gets pushed back, the H gets pushed forward here. How do we get neutral compound, neutral product? Br minus, which was the leaving group, takes the H, leaves it behind. And what do you get? Hopefully you wrote sort of somewhere so you can put some here. Hopefully you already got the answer here. You get a product that looks like, we can draw it like this and maybe say racemic. That would be clear. What does this mean to you? That's chiral right there. What does racemic mean?
50-50.
RNS, 50-50. I mean, or you could draw them both out. Over here, someone did bolded and then said plus an antrim. Okay? Racemic, right? SN1, carbocation chemistry. How about if we treat it with KOH in heat? What's that product going to be? Stronger weak base or stronger weak nucleophile? Strong, it's an anion. Most anions are strong nucleophiles. There's some exceptions. I mean, chloride's not that strong, but hydroxide's strong. So what's the mechanism? SN2. Can you do SN2 on this halide? Yeah, secondary, you can do both. So what do we got going on here? Hydroxide. See, hydroxide is a bully. It's not going to wait for that to ionize. Here I come. Boom. Concerted, kick it off. What's the product? Is it going to be racemic? No, it's going to be inversion. This here is, what's that, S? That's going to be R only. right? We did SN2 with inversion. Those look pretty straightforward, what we've been talking about. You have to assess nucleophile, you're going to have to assess substrate, okay? And we haven't covered elimination yet. Once we cover elimination, you're going to have to say, okay, is this substitution or elimination? How about over here? React this 2-iodo-butane stereochemistry with methanol and heat. SN1 or SN2? SN1, methanol's weak. Methanol's too lazy to do SN2. This is going to be boom, boom, boom. O and me, and it's going to be racemic. I mean, that's just like up here, right? I don't expect any rearrangement. We're going to ionize, make secondary cation. I mean, it can't rearrange to any better than that. The oxygen has, here the oxygen had 2 H's. We lost an H, got an alcohol. Here it only has 1 H. When you lose an H, you end up with the methyl left, and it happens to be an ether. Nothing tricky there. You just... Questions about that one? So what was that, SN1? Just like up there, ionization, methanol attacks, then I takes the H. We made that bond right there. That's going to be both R and S. So this is not a stereo selective reaction. How about over there was? These two not stereo selective. How about over here? Unimolecular or bimolecular?
SN1.
It's a tertiary.
Based on this, SN1 or SN2?
SN2.
SN2, it's strong. It's going to be a bully. Based on this, SN1 or SN2? SN1. So this one, can this do SN2? No. But that only wants to do SN2. So what's going on here? This is a little conflicting. No, you're not going to get SN2 there because it does what anyway?
SN1 anyway.
No, this is a bully.
SN3.
E2. E2. Strong base / nucleophile will always be my bimolecular. Look on the previous page. Didn't we say that? In this case, can't do SN2 because the substrate doesn't do SN2, right? So what's the other bimolecular mechanism? Well, it turns out it's going to be E2. And that's what we're about to do. Yes, that's E2. Classical E2. Is there anything else here? Reagents. I usually end this handout with that, and then we move on and say, okay, let's look at E2. Let's look at this first. What reagent would give this transformation?
Bromius, methyl bromius peroxide methyl.
Tell me again.
Like an iodine and that's bromium methyl.
An iodine of a methyl. I drew it sort of backwards. I mean, you could draw it like this, but I want to make sure that the iodine is bonded to the carbon, not the H's, right? So it's the same thing. But what else do we need?
NaOH.
NaOH, what's that going to be?
Protonated, I mean.
No, this is regular alcohol. So hydroxide is not strong enough to do.
HCl.
The I would
Or
take.
H I.
Once the I leaves,
HI?
Yeah, H I.
HI to do what?
Make the oxygen possibly charged to the leave.
The oxygen isn't leaving though, the I.
But the iodine would be a nucleophile. We don't have iodine in the product.
Energy.
It's actually two different ways here, as I say over here. You are kind of mixing the two different ways. This is one way, but what do we need first? So hydroxide was along, but so hydroxide is not strong enough to deprotonate this. We said that last time, right? If you want this, what are you envisioning here? This reacting with that?
Yeah, the I leaving.
So this would be nucleophile. This is the group carbon leaving group. Is that a good nucleophile? I will make that a better nucleophile. T? Hmm? Pure sodium, yes. What does sodium 1 do to the alcohol? It makes the alkoxide, right? You got to look back at the previous class notes, right? Right? Okay. Sodium does this. Now we throw in this, which was suggested. And what will this do? Kick off the iodine. We put a methyl on the oxygen. Oxygen now bonds to methyl. Isn't that what we want? Yeah? So you first make the minus, and then you throw in your, my favorite term of all time. This is a carbon. Is that carbon electrophilic or nucleophilic? Yeah, it's electrophilic. That's why the nucleophile attacked it. It's a carbon electrophile. Huh? It's not what? It's a carbon electrophile. That's not the funny part. The funny part is every time I say carbon electrophile, I think of carbon electric. See, you guys don't even know who carbon electric is. Okay. I think I told that joke before. But I do. I always think of carbon electric. What do you call this sequence when you turn the alcohol into the ether? Named after an English chemist. Williams and ether synthesis. Okay, so there's the Williams and ether synthesis. There's another way to do it. That was with the oxygen. Was the oxygen the leaving group here? No, we put something on the oxygen. Can be done with OH's leaving group or without. That's without. How do we do it with OH being a leaving group? What do we want to place the OH with? OMe. How can we do that? How do we make this a good leaving group? Somebody said acid. Acid. So we need H+. What do we want the nucleophile to be? Methanol. Okay? If we can protonate this with H+, can you envision this then leaving and getting this? Yeah? Now what can attack this? Now methanol can attack it. And we get O-M with an H. Now suddenly you can take the H. What acid do you want to use here? HSO4 minus here. And this can take the H, leave it behind, and you reform your H2SO4 catalyst. Somebody mentioned HI earlier. I thought you were doing this. You don't want to use HI here. Why not? Because the I minus will attack your cation. Sulfate will never do anything in organic 1 or 2. So if you just want to use the strong acid, you got to be careful about what's the minus there. Your halides will act as nucleophiles. Sulfate, phosphate, or F minus will not. We did that when we were doing some alkene reactions, right? Did we do that somewhere? Yeah, when we were adding hydrating and alkene, you don't want to use HCl, you'll get the alkyl chloride. HF is okay though. Do you see the two different ways? Up here, that oxygen is still there, we just put nothing on it. Here we replace the OH with an OMe. See the two different ways? Yep. I'm going to skip the middle one. That's just a plain old O-alkylation. You do have stereochemistry. You can do that one on your own. How about this one down here? Lincomycin. You've looked at it. The difference is right here. What reagent would do this? HCl, yeah. What we just talked about. You protonate it. It's either, is it going to be SN1 or SN2? What do you want it to be? Why do you want it to be SN2? Because we want inversion, right? We hope it goes SN2. If it goes SN1, can it do SN1? Secondary could. If it decides to go SN1 for some reason, we're out of luck because then it would become racemic. It probably goes SN2 because probably somebody took this and heated with HCl and got that product. Mother Nature just chose to do SN2. Something about it, the way it was done, I'm sure you can make it go SN1. But I've heard of clindamycin, Cleocin, it's given like for outpatient procedures or something, IV, hospital, yeah, nursing. It's more active than lincomycin. These are natural products. Well, that's synthetic. It's made from a synthetic reaction. This is natural product. It's made from microbes. It's isolated from microbes. But then they did some chemistry on it, and that's a better antibiotic. Lincomycin was discovered in Nebraska. Anybody know what city?
Lincoln?
Lincoln, Nebraska. Yeah. In the dirt. Microbes that were just in the dirt, they back in like the 1930s or something, found that it had antibacterial properties. Okay, on the back side is another antihistamine synthesis. Here's another SN2. Bam, kick off the leaving group. OH is not a good leaving group. See, there's no acid here. That's a base. Kicks off the leaving group. They didn't throw any iodide in there. They could have. There's other SN2s up there. Oh, here's a good question. Yeah, I always like to ask this question here. We've already said what's the purpose of the base in the previous one. Here's a product shown down here, but this, which nitrogen's basic? On the left. The other one, the lone pair, is in a p orbital. Now they're doing two steps here, and they're not showing the product after the first step. The first step is the SN2. This attacks here. I say likely SN2. Can you do SN2 at this carbon? It's secondary, yeah, you can do it. After they do that, they then cleave this group off over here. That's why it's going over there. That's the second step. In the first step, I say it's likely SN2. But how would we confirm that? How would we confirm it's SN2? And why does it matter? First, how would we confirm it's SN2?
Experimental.
Do I mean experimentally?
Yeah.
I do mean experimentally.
Whether it's optically,
Do you know
Now-
whether
whether
it's
it's optically active or not.
Yeah, let me come back to this because this sounded good. Tell me.
Whether it's optically active or not, because if it's racemic, it won't be optically active.
Yeah, well, they apparently have racemic here, so you're going to get racemic there because R is going to give S is going to give R, so you still have mixture. You could make this specifically like R,
Here.
and then do it and see if you get S in the product. Yeah, you could build in some stereochemistry. You could say, does it give inversion or does it give racemic? Okay, yeah, that is one way. Somebody over here said something else? What's another way? How would you confirm it? We talked about other. Go ahead. I don't see how mass spec's going to confirm a reaction. I mean, this is a product either way. It's not going to confirm the mechanism. Well, the intermediate is really what I'm talking about. I could show it. How do we know that the first step is SN2? What about rates, reaction rates? How would you do a couple of experiments and develop experiments to use rates to determine SN2? Concentration of what?
Nuclear file and the electric file.
And what would you do? Explain the experimental design.
You would leave one constant and change the concentration of the other one. You just only change one of the concentrations at a time.
So which one do you want to change? You've got your nucleophile and you've got your carbon electrophile.
Nuclear file.
Okay, and if you change the concentration of this, let's say we do the reaction twice, once with a certain concentration, and then let's double it. If we double the concentration and the rate doubles, what's the mechanism?
SN2.
SN2. What if we double the concentration and the rate doesn't change? Sounds like it might be SN1. I mean, it's certainly SN1. I mean, right? So you have your rates. So we talk about rates. Why does it matter? Well, if it's actually SN1, and you say, hey, boss man, or hey, colleague, I want to double this because I want to increase the rate, and then you spend, on huge scale, $10,000 more to use double this, and it really didn't do anything, they're going to say, why did you suggest to spend $10,000 more? So you can't just blindly start doing something when maybe doubling that's not going to have an effect. So stating it as SN2 is basically stating that both of these affected, and now I know, hey, I can speed this up by doubling the concentration of that, and we won't be wasting our money. So that's why you want to know, SN1, SN2, what's going on. Okay. So stereochemistry is one way to judge, but also rates, and right? We have two different rate equations. Well, now it's time for E2. Elimination. And elimination is the opposite of what? We're going to eliminate something from a compound. It's actually the opposite of addition. We did addition with alkenes. We had alkenes and we added to them. Well, guess what we're going to make when we eliminate? What are we going to make? If you go backwards from addition, we're going to make alkenes. Elimination reactions give alkenes. You can actually, this may not be drawn out, let me just show you, okay? If we take this, we add HBr, that's plus HBr, what do we get? Maybe that? Final exam is in 3 or 4 weeks, right? It's an addition reaction. So we add it, that's what the plus sign means. What if I eliminate HBr? What would we get? Minus HBr. That would be eliminate. Okay? We eliminate HBr. So this is a cycle here. So what we're going to be talking about now, look at this guy. This looks like a tetrahedral carbon with a leaving group. A month ago this was a product. But now, going this way, it's a starting material. And for the past week and a half, we've been doing chemistry with tetrahedral carbons with leading groups. But before, we were replacing them with something, substitution. Now we're going to eliminate, and when you eliminate, typically you get alkenes. Now you can have sophisticated chemistry where maybe there's a nitrogen here, and when you eliminate, you actually get a carbon double bond in. Yeah, that's not an alkene, but the basic eliminations typically do give alkenes. So let's look. On the front page, there's one in a drug synthesis of Tamiflu. Flu season coming up. Starts with the Diels-Alder, but somewhere down here, right here is an E2. Right here we have iodine. Now we have this alkene. What's eliminated? HI. Because now there's only one H there. There's two there. So we eliminate the HI. Get the alkene. And so if we came this way, we would add HI. We're eliminating it, but in the alkene. From there, they do other chemistry. They're using DBU. DBU is a base. We're probably not going to see it. It's a nitrogen base. You can look it up on the wiki. THF is just a solvent. Reflux, 12 hours, 96% yield. There's also an E1 reaction, E1 elimination down there. You can look at it. It's a little bit more complex because there's intermediates, etc. But let's look at it. Elimination. Okay, our heading up here. Beta elimination. Beta elimination. Out of tetrahedral carbon. Just like with our substitution handout, we're going to introduce this very analogous way. First, I'm going to show you a general line reaction. Tetrahedral carbon with a leaving group. You've got to have a base to do an elimination. Of course, bases can also be nucleophiles, so they have dual character. Beta elimination. Why is it called beta elimination? Because the H that's removed, we do remove an H. The H is not on the first carbon or the carbon where the leaving group is. And the first carbon is called alpha. The H is on the beta carbon. So the beta refers to where the H is. We do an elimination. We're going to put in a double bond. What are we essentially losing? We're losing the H and the leaving group. Because over here, that carbon has two H's, but now that carbon only has one, and the leaving group is gone. So we've lost an H and an X. The base is going to take the H. The X is going to come off just as a leaving group. Now, what is said here is probably pretty much what was said in the substitution. Okay, not much more to say about the leaving group. Let's look at a specific example. We take this alkyl bromide. We take this alkoxide. Looks a little hindered. We can do this. We can eliminate and get our alkene plus the leaving group, and the base now has the H. So let's look at two possible mechanisms for this. We'll do both E1 and E2. And I've redrawn the same reaction. Let's first do E1. First step of an E1 is the same as the first step of an S1, which is what? Ionization. Let's ionize this. What do we get? Hopefully you already see that this is a bad mechanism. This is not the right one. Why is this not going to be the right one? Because we've got a primary carbocation. But I'm still going to show you what an E1 looks like. Okay? Ionization. Because when all this happens, the leaving group, we do have to form that. So what does this give? It gives that plus Br minus. Well, there's one of our products. Leaving group just is gone now, right? What else do we have to get rid of here? One of the beta hydrogens. There's two there. Two there. Beta hydrogens. Later on, you won't be able to, some of you won't be able to identify the beta hydrogen. Where's the beta hydrogen? Not on the carbon leaving group, but it's next door. All right? So don't just gloss over it. You got to recognize the beta hydrogen. What do you want to do next? It's really, well, somebody tell me what we want to do next to get to where we want to go. Oxygen take an H. I mean, what else would you do? Okay, well, you could do it two ways. We're going to do two arrows here. This takes the H. This acts as a base. Bases take H's. That bonds to the H. These two electrons, where do you want them to go to get the final product? They come in and move in and fall in as a pi bond. What does all this give? It gives that. Pi bond in gives that. When this takes the H, there you go. This is going to be the slow rate determining step, ionization. This is fast, relatively. It's called ionization. What do you want to call this step over here? Yeah, I mean, you can actually call that the beta elimination. I mean, that's the individual. We're eliminating the beta hydrogen. Or you can call it something like base abstracts beta H. But that's fast.
Why does the oxygen minus charge not go to the plus charge?
Because they're doing elimination. Really, because they're doing elimination. The question is, why does the oxygen not attack the cation? Well, if it did, that would be an SN1 mechanism. What we're going to find is, in a lot of cases, both mechanisms can occur. They could. A lot of reactions give mixtures of both your elimination product and your substitution product. We'll eventually talk about how you make one preferred over the other. It's a good question. Now, the mechanism I'm doing is not reasonable anyway because we don't want to make a primary cation. I'm showing you in E1, but I'm eventually going to tell you that this is not the mechanism for the model reaction. When we do E2, that's going to be the one that's going to work. Remember, never do primary cations. So, this is a two-step ionization, and then you eliminate. Put in the pi bond. SN1, you ionize, and then you attack the cation. Now you could do a reaction coordinate diagram. This is your, how many intermediates here? One, you draw a high intermediate, rate determining step towards it. Fast, falling downhill is easy. It's not going to take much activation energy. Question. Let's look at another way to do this. E2. This is going to be concerted. There's your beta hydrogens. Here we go. In this case, it's all going to be one. It's all going to be here. The base takes the H. These come in. That gets kicked off. 3 arrows. All happens at the same time. What does all that arrow movement give? Gives all that. Base taking the H, that's the thing on the end. Electrons that used to be bonded to the H move in, make pi bond, there's that. And when they move in, they essentially kick off the Br, and it leaves taking the electrons with it, and then you get Br minus. Okay? It's all concerted. How many intermediates here? None. No intermediate. Not, at least not in this model reaction. Where's the carbocation? There's no carbocation. Just like there's no carbocation in SN2. SN2 and E2 don't have carbocations. But SN1 and E1, that's carbocation chemistry. So which do you like better, E1 or E2 for this?
E2.
Good, E2, because primary cation's bad. Yeah, this is a good E2. The base / nucleophile, is this strong or weak? Strong, it's an anion. So since it's an anion, we said it would be bimolecular. We need to say why it's bimolecular. Why is this bimolecular? Okay, here's how many steps in this mechanism? One step. Which is the rate determining? That one. Which, are these both involved in the rate determining step?
Yes.
Yes. So that's why it's called E2. Okay? They're both involved. It's only one step. They have to be both involved. How about when I showed the E1? What was the rate determining step there?
Ionization.
Just ionization. Was the base involved in the ionization? No. The only thing involved up there in the rate determining step was just that guy ionizing. That's why it's called E1. Okay, this is strong. We said on the other page, if it's strong, it's going to be bimolecular. No, E2. That's another reason that this model is E2, because we're using the strong base. Strong bases do E2. Weak bases give E1. Okay. Another possible elimination mechanism. I just sort of added this in to this handout here. There is another possible mechanism to show. Somebody, I'm going to just go ahead and show you. Anybody thinking of another way? We did it two different ways. Is there a third way to get to those things?
Could the oxygen electrons attack the hydrogen first?
Very good. What we did not show is this taking the H, instead of doing everything conservative, just leaving it behind, and just do a simple acid-base reaction. That's a carbanion. Did we form a carbanion on our other two mechanisms? No, we did not, so this is different. What could this then do to get us? That right there gives you your alcohol. What could this now do? Sort of, it's analogous to back bonding. Move in and make pi bond, kick that off. What does this give us? There. This is neither E1 or E2. It may not be in your textbook. And I have to think why it's called. This is actually called an E1 CB. And I've never quite understood why it's E1 and not E2. It's E1CB. The CB stands for carbanion. Carbanion. This is the last you'll see of E1CB in this class, this semester. Okay. E1CB is I think probably covered in advanced organic. It's a third very unique mechanism. Important to know right now is neither one of the E1 or E2 involves a yeah, that right there is very difficult to form. That's just a plain carbanion. It has no stability. And in the other two mechanisms, we didn't form such a thing. This usually operates whenever your carbon is pretty acidic for some reason, and you can make the carbanion. But we're not going to see it in this semester here. But that is a third one. You can look it up if you want to see more about the. And again, I've never taught a class where I taught E1CB, and so I never really had it in grad school or anything. We didn't ever look at it too much. I'm not sure why it's E1 and not E2 CB. Okay, that's that there. An alternative example. If we take this here and heat it in just T-butanol, it's not really, this can be considered a solvent. T-butanol, neutral, or no solvent at all. Just heat this guy. You get that product plus HBr. Well, in my example, I'm not showing it. Let's just look at the potential mechanism. Obviously, it's an elimination. I agree? That's the first thing I want to recognize. It's an elimination reaction. We eliminated HBr. Okay, two mechanisms, E1 or E2. Forget about the third one. Does this look like E1 or E2? E2 and SN2 both require strong bases / nucleophiles. Is that a strong basis / nucleophile? Can't do bimolecular. It has to be unimolecular. Since we're doing elimination, the unimolecular is E1. Okay? This is a weak base equals unimolecular equals E1. Since it's E1, what's the first step? Ionization. Can you ionize and form a secondary cation? Yeah, secondary is okay. Plus Br minus. What do you want to do next? This can take the H, come in, and you get the products. See, the leaving group can act as the base. And if it did, you can bake HBr. That's almost not even needed. Your weak base sometimes is not even hardly needed. It just acts as a solvent to dissolve everything. And in fact, if you heat this, if you get that up to about 200 or 300 degrees, it'll probably decompose, form this, and eliminate HBr by such a mechanism in E1. Okay. Entropy. Is this driven by entropy? Yes. One molecule going to two. Eliminations are driven by entropy. Since it's driven by entropy, is heating going to make them go faster or slower? Faster, because in your free Gibbs equation, temperature magnifies which term? Entropy term. So if entropy is favored, how do you make it even more favored? You magnify it by increasing the temperature. Yeah. So you heat these things and they'll eliminate. Is it thermodynamically favored? And we can pull out our calculations. But what are we doing here? We're going from two sigma bonds, sigma bond to H, sigma bond to bromine. What are we making? Pi bond. Is pi bond stronger than 2 sigma? No. Thermodynamically, it's not favored if you do a calculation. So if it's not favored thermodynamically, does it happen at all? Yeah, it can. Yeah, if it's hot enough, you can put in the energy. Yeah. I hope you don't think that non-spontaneous reactions can't be performed. So, make sure you understand thermopy and entropy. We've talked about that before. It's basically just sort of a reminder of looking at this new reaction. Okay, that was the introduction. Just like with substitution, we're now going to talk about various aspects of the elimination reaction. Question?
When you're taking the beta H, does it matter which direction you go? Does it just be one away? Would it be the most stable, or?
In my examples, there was only one beta hydrogen carbon, one beta carbon.
Was it?
Maybe not. No, you're right. In the last one. Yeah, you're right. You're right. very last one had 2. Yes? That's the alpha carbon. That's the carbon with the leaving group. What she's saying is, those are beta hydrogens there, but these are also beta hydrogens. Why not take this H and put the double bond in here? We're going to get to that on the next page or 2. This is the more substituted alkene, so it's going to be more thermodynamically favored. The transition state leading to is lower. But in some cases, we don't get the most substituted alkene. Basically, this is all the next episode. Okay? Remember at the end of Batman, they'd always show you what's coming up next? And then say, stay tuned. Same bat time, same bat channel.
I don't think anybody here remembers that,
Nobody here remembers that?
except for maybe me.
Uh-huh. I didn't watch the originals. There's reruns for me. Anybody ever seen the real Batman that was made in the 60s and with Adam West and
Just reruns.
Ward, what was the name? Robin Ward, Wayne something?
Remember Adam West.
Yeah. And then there's the old 4th grade joke. What do you call Batman and Robin after they got run over by a train? Flat man and ribbon. Okay, let's look at various things about this. There is a good amount to look here. Look at here. The idea of regioisomers just came up. Is this the right page?
Yeah.
Next page. If this undergoes a beta elimination, there's only one possible product. Because there's only one beta hydrogen. Okay, there's 2 there, but either one, they're identical. So eliminating either one, you remove HCl, you're going to put double bond in right here. And there it is. And there's actually no stereochemistry there because that's not a stereogenic alkene. So that's the only regioisomer and only stereoisomer possible for a beta elimination. But if you take this substrate, you've got beta hydrogens on each side. And so you can remove HCl over here, put double bond in there. But you can also remove HCl over here and put double bond on over there. And this guy actually is stereogenic. It can be either E or Z. So there's 3 possible products theoretically. These 2 and this one being regioisomers, these 2 being stereoisomers of each other. So, which alkene will be formed in this reaction here? It depends on a variety of factors, including mechanism, base, orientation of groups in the starting material. That is the stereochemistry in the starting material. So let's look at these various things. First off, we'll start with the easiest. We already know this opening statement. The most substituted alkene is the thermodynamic product. Right? Because the most substituted alkene is the most stable. The most stable is the thermodynamic product. In the context of eliminations, that's called the Zaitsev product. Okay? When you're doing eliminations and you say, here are my alkene products, the most substituted is also called the Zaitsev product. Now, Zaitsev is spelled 1,000,001 ways. Sometimes it's spelled with a Z. I spelled it with an S there, etc. There's about 2 or 3, 4 different spellings. Now, the Zaitsev product is always the major product with an E1. If you're doing E1, the major product is Zaitsev. That is the most substituted. Not only is it the most substituted, but it's also the most stable isomer of the there. So if the reaction up there that gave 3 products was E1, which product would be favored? Which of the 3 is the most stable? These 2 are most substituted because that's mono-substituted. But of these 2, which is most stable? Trans, the group's opposite. That goes back to rotation and stuff. This is your E1 product. Okay? Take home. E1, you always get the most stable alkene product. Including regioisomers and stereoisomers. Because E1 is ultimately thermodynamically controlled, and you get lots of equilibrium going on, and you just get the best one. So that's the easy. E1 is the easiest. For example, if you take this guy here and just heat it in water, what's the product going to be? Well, you need to be able to show all possible ones. I'm showing this one here. That's coming from taking this beta hydrogen and the Br and putting the double bond in there. Okay? If we took that beta hydrogen, we would get that alkene, right? I'm going to call this A. That's the A taking the A hydrogen. If we took the B one by either mechanism while we're doing E1, that would give this. In terms of name, this is called what product? Zaitsev. And this one's called what? We haven't named it yet, have we? Hoff. It's up there, but we didn't name it. The less substituted is called the Hoffman product. So this would be Hoffman. It's not the most stable. What mechanism are we doing here? Do we have a strong base? No. So there's no strong base. What are we doing? E1. It's already up there. Which product does E1 give? Zaitsev. Most stable. That's why I drew it. Does this product have... Okay, this is not right. Something's been wrong. This was wrong last time. I didn't correct this handout. This alkene is not stereogenic. Okay? I think what happened is it used to be stereogenic, and somehow I changed it for some reason and didn't take out that. That alkene's not stereogenic. So you don't have to worry about stereochemistry. Okay, so there you go. You wouldn't get this product as major. What about E2? Well, E2 is more variable. It's not as straightforward. E2, you can get either. E2, sometimes you get the Hoffman. Okay, E2, we're going to need a strong base, so I'm using hydroxide here. If I extract this H, that leads to this product, which is the Zaitsev product. It's easily formed with an unhindered strong base. Unhindered is important. Let's look at the two H's. Here it's taking that H, which up there we call what? A? here we're taking B. Which H, A or B, is the most accessible? The most sort of out there in the open? B. B is more out there in the open. Because it's sort of like on a primary carbon. That's sort of buried in there between methyls, because ultimately it's on a tertiary carbon. An unhindered base has no problem extracting the more hindered beta hydrogen. Unhindered base has no problem. But if we start using a hindered base, see, I put these groups over here, like wings. It's going to start causing hindrance. And I can't come in, I've got to come in exactly right. This is called a sterically hindered base. It's going to have a hard time extracting this H. The more hindered your base, the more likely it is to take that H, the more accessible one, and that actually leads to not the more stable product, but it leads to the less stable product, which is called the Hoffman product. Sterically hindered bases typically give the Hoffman product. Now this is also called the kinetic product. It's not the most stable, so you wouldn't call it the thermodynamic product. That's the thermodynamic product. It's called kinetic because in this situation, it's just extracted faster. Because the base can get to it faster and easier. So it happens faster. So that's why it's sort of termed the kinetic product. But more commonly, it's called the Hoffman. So take home from all this, the bulkier your base, the more prone you are to getting the Hoffman. Now, there's an even bigger consideration here. Second is there's a stereochemical requirement for an E2 elimination. Whenever you do an E2, which is a concerted process, the leaving group in beta hydrogen must be coplanar. With anti-coplanar being very much preferred over syn coplanar. Remember something like anti-coplanar? Here's the H and the Br in a simple. What type of figure or projection is that? What is that called? Newman. Remember the Newman? The Br and the H would be anti. Is that right? Ring a bell? They're also coplanar, because that's the plane right there. They're both lined up plane. It's not like one is like this and the other one's like this. I mean, if the plane is here, one's here, the other one's in that plane too. So that's representing anti-coplanar. Or commonly shown here. But we're going to go back to Newman's. This would be more syn coplanar. Which one is highly preferred? Anti. Very highly preferred. Doesn't mean syn coplanar can't work. We're also going to look at rings. And here, the Br and this H are anti-coplanar. One is straight up, one is straight down. That Br and H are not. So with this eliminated, you would eliminate that H and the Br. Now importantly with the rings, the leaving group must be axial to be coplanar. Because if we do a ring flip and put the Br equatorial, which of the beta hydrogens are anti-coplanar to that bromine? Bromine is there. Which H is projected like that of the four? None. But here, bromine is straight up, so which one is straight down compared to that? What I underline. When the bromine is axial, none of the H's are coplanar. The bromine can only be eliminated. I'm sorry, I should have said equatorial just a minute. When the bromine is equatorial, none of the H's are coplanar. You only get a coplanar H when the bromine is axial. Now, is axial the best position for the bromine? No. It actually can only eliminate from the worst position. We'll do more of that, but that's sort of an introduction to coplanar. We'll do this by doing some examples. All right. We're revisiting stereochemistry. We're going to revisit Newman projections. What's the product of this reaction here? First off, is it substitution or elimination?
Elimination. Because it's a strong profile and tertiary.
Okay, well that's weak. That's strong, and it's there, and it's going to do its thing. Strong nucleophile slash base. We call it a nucleophile if it attacks a carbon. We call it a base if it attacks an H. But it's strong. It's hydroxide. So since it's strong, is it going to be unimolecular body? Ionization. So it's either SN2 or E2. So which one is it? SN2 or E2? I hear E2. Anybody else? Anybody like SN2? Why is it not SN2? Because it's a tertiary halide, and you don't do SN2 on tertiary halides. Right? You don't do SN2 there. So what is it? E2. See, that's how you have to assess these reactions. I have a question about how I arrived at this being an E2.
You say you can't do it on a tertiary halide?
You don't do SN2 on tertiary halide. Didn't y'all all repeat that to me one day? It's E2. So now that it's E2, show the product. You first have to assess, okay, what mechanism I'm going to do. Now you do it. Question?
Do we look at what is also under the area for tertiary, or do you look at the actual reactant?
No, when we say tertiary halide, we're talking about the leaving group thing. Br is your leaving group. This is just solvent. That's isopropanol. That's just solvent here. This is your substrate with the leaving group. The leaving group, if it's on a tertiary carbon, you can't do SN2. I mean, is that a leaving group? Could be if there was acid around. You see any acid? So it ain't going to leave. Okay, so it's E2. We're doing elimination, a beta elimination. How many different types of beta hydrogens are there? Different types, not total, but types. That's the alpha carbon. That's a beta carbon. There's one H there. That's a beta carbon, right? How many H's on that one? So what's the answer? How many different types of H's? Where's the other one? Yes. See, you guys and even me often forget this. You think, oh, that's just a group coming off. It's actually a carbon, and there's 3 H's there, and that's a beta carbon. Now, they're all three the same type. There's 2 types. That means you can get alkene here and there. Can you draw all possible alkenes from beta elimination? Draw all possible ones. Just theoretically, if you do a beta elimination. Then let's look and see which one we're going to get. Don't worry about the stereochemical requirement. Safe step Hoffman. Just draw beta elimination problems. Then we'll eliminate the bad ones. label these. This one is A, and those down there is B. This one, label one is B. I'm going to do the B one first. If we eliminated the HB and the bromine, what would we get? Little bond like that. I mean, this is that coming off. That's now a double bond right here, right? There's no change in stereochemistry here. That's no longer tetrahedral, it's now planar. Does that have any stereochemistry, the alkene? No. It's not stereogenic. Is this safe there for Hoffman? Hoffman. Let's substitute. Okay. How about if we take HA? We're going to get double bond sort of there. That carbon is now planar, so I'm drawing the ethyl just planar and the methyl planar. The other carbon, bromine used to be here. What's now this carbon? A methyl and a T-butyl. Methyl and a T-butyl. Hopefully you see that. Does this have stereochemistry?
Yes.
Yes. This is what? E or Z? E. You also potentially could draw have the T-butyl and the ethyl on the same sides, that would be Z. There are your three possible theoretical beta elimination products. We're doing E2. Does E2 give 1 always?
No.
E1. If we were doing E1, it would be that one. We're not doing E1. What are the two things that affect the E2 outcome? Size of the base. Well, it has to be strong. We're doing E2. If it was weak, we'd be doing E1 and we'd have the product already. Because E1, you don't have to think about it. Is the base hindered or not? Hydroxide.
Yes.
No.
Hydroxide is one of the smallest bases. Is hydroxide going to have any trouble getting HA? No, it's not. I mean, you'd rather form E if you can. But here's the bigger kick. How does AHA and the bromine have to be oriented when the elimination takes place? Coplanar with what preferred? Anticoplanar. How can we see the anticoplanar? Now your book may tell you to look at this one way or other. We're gonna do Newman. We're gonna make them go up and down. We're going to put this in a Newman projection. Remember Newman's? I'm going to stand over here. I'm going to look through there. Circle, circle, dot, dot. What's on the front carbon? I see something coming straight down. What is that? Methyl. I'm going to call that Me. There's something on the front carbon coming towards you guys. What is it? Ethyl, so that's on my right. It's coming out toward you guys. If I'm looking that way, it's on the right, so there's an ethyl. And the H is thus, if I'm looking, going behind the board, so if I'm looking this way, behind the board's on my left. So there's the front carbon. Now let's look on the back carbon. On that back carbon over there, there's something going straight down. What is it? T-butyl. It's actually eclipsed with the methyl. Okay? I'm going to have to, okay, they're eclipsed. What's on the back carbon coming towards you guys, on my right? Methyl. See, these are all eclipsed. What's on the back carbon going behind the board? That's my left. Bromine. Okay. Don't forget, which one is HA? There's your two that are eliminated. They're actually planar. They're both in plane, but they're not anticoplanar. They're syncoplanar. This thing's going to have to rotate to eliminate. It's going to want to rotate because it wants to eliminate anticoplanar. Let's rotate. You can rotate either one. I'm going to rotate the front carbon. I'm going to rotate this. I want the H coming over here. And when I rotate it, let's get rid of the Hoffman. So that's not going to be the product. We're rotating the front. I'm going to rotate it 180 degrees. I'll put HA here. Put methyl straight up. Ethyl there. The back we're not going to rotate, so the bromine is still here. The methyl on the back is still there. And then what else is on the back? T-butyl. Now the bromine and the H are anticoplanar. Here's sort of the center, the anti. Okay, if I just turn this, the bromine would be straight up, the H straight down. Okay, if I just turn it, it'd be like I showed you. It'd be like that up there, without the other groups. That's how the elimination takes place. The hydroxide takes the H. The electrons move in between the two carbons, which we can't see, and kicks off the bromine. And that's all concerted. And when the double bond is put in, these groups are there. That is, the methyls are on the same side. And the T-butyl and ethyl are on the same side. Which product is that? Z. Methyl's on the same side, the other two groups on the same side. This reaction actually gives Z as the major product because the anticoplanar is highly preferred. Is this the best conformation? No, putting these big groups next to each other, not the best conformation. So what makes it preferred? Nobody asked why it had to be anticoplanar. Anybody ask why anticoplanar was preferred? Why didn't you ask that back then? Why is anticoplanar preferred? It's because it's almost like, how do you do SN2? When SN2 attacks backside? See, when the base takes the H, these electrons come in almost like backside. And if you really get into the orbital stuff, which you remember the big thick book, somewhat analogous to this coming in backside. That's why the anticoplanar is highly preferred. Syncoplanar does work though. Okay, do the remainders. I recommend doing, see how I did it? Newman, rotate it, and then when the reaction takes place, the groups are fixed. So did we get the best product? No. D is the best. Okay, guys. Have a good evening in lab and tomorrow afternoon. See you on